Welcome to a class on linearization of nonlinear models. So when we think about differential equations, we can think of them in terms of ordinary and partial, but we can also think about them as being linear or nonlinear. When we think about four examples here, we want to describe and see how might we see them to be either linear or nonlinear. So the first example that we show above, we have dy dt plus y equals x. So in each of these terms, we have an order of the derivative of the output y plus a y equals x. Now we've already grouped the y onto the left-hand side, but when we look at this, we see high linearity of the right-hand side, meaning that we just have x. We also know that we have linearity in the y, in that it is a singular linear function. We can take that, and if we performed the derivative on everything, we would then get d squared y dt squared plus dy dt equals, so on. But when we think about this example in particular, we can see this as a standard linear expression. So we know this one is in fact linear. The second one, unfortunately, the difference is now y has become sine of y. So sine of y is a nonlinear function. Therefore, this is going to be non-linear. The left-hand side matches the example number one, but the right-hand side is x times y. So if we wanted to try and group our y's on the left-hand side, we could divide everything by y, and in doing so, we would end up, though, with 1 over y times dy dt plus 1 equals x. Now the plus 1 equals x part is linear, but 1 over y dy dt, unfortunately, that is not linear. Therefore, this is also going to be termed a nonlinear expression. And finally, y dy dt plus y equals x squared. Well, there's two parts of this that make this nonlinear. The y times dy dt and the x squared term. Now, in theory, we can linearize both of those, but unfortunately, this is still a non-linear expression. And so seeing these, we have ways of linearizing a nonlinear expression based on what we learned back in calculus. Specifically, we can take these and apply them into transfer functions by first linearizing them using a Taylor series expansion, which we're going to formally define really quickly. So a Taylor series expansion, you may remember, because a Maclaurin series is a Taylor series set at a standard x equals 0. But Taylor series is based on an infinite sum for a polynomial that allows you to essentially describe any type of function f of x based on that standard term. Now, the further away you go, the more complicated it would be to truly describe it, and you would have a lot of deviation. But in theory, as you keep adding more and more and more terms for the polynomial, you should be able to actually continue describing that function. So in a Taylor series expansion, which is based on any real and complex valued function that may be infinitely differentiable around some point, xs is going to be our set value of x that we're going to be considering around, we can define a power series as f of x equals the sum for n equals 0 to infinity of any function f to the n of our set value x of s over n factorial multiplied by x minus xs to that same n. And now this is a standard function, but really we could describe this a lot more easily. Taking our Taylor series expansion here, we're going to actually now expand that out based on this expression. So this f to the n of x of s is based on the nth derivative of the function f based on a set point value at x of s. So let's try plugging in several of these. Let's try f to the 0 of x of s over 0 factorial x minus x of s to the 0. It's a summation term, so we're going to add the first derivative at set value x minus x of s to the 1 plus the second derivative x of s, I almost wrote f, x squared, x minus xs squared, plus so on. So after that point, these are going to start going into the higher order terms. But when we take this value on its own, what we're really seeing that this becomes is assuming, of course, that we just are going to focus on the first two terms for right now and assume that these get very small, this will end up becoming, on a first order approximation, this entire thing, f0 of x of s, is simply just the function itself, because it's the 0th derivative, so the actual function, set at x of s over 1, because 0 factorial is 1, multiplied by x minus xs to the 0. Well, that entire term is 1, so just the function itself at the steady state or set value. We're going to add that to our first derivative term here, where this will be then the derivative of f at, based on x in this case, because that's what our function is based off of, at x equals xs, multiplied by 1 over 1 factorial, still 1, now multiplied by x minus xs to the first, which is just 1. And so really, we can think about a standard first order linear operation being this. Now remember, the second order and higher order terms do in fact exist, but we're assuming for right now that we're going to take just a linear approximation on the first order. If we add to the second order, then maybe that would then become now d squared of f dx squared at x equals xs times x minus xs squared over 2 factorial, which is 4. But for right now, we are going to assume that this second order term is going to be excluded. Okay, so because of this, we can take linear approximations of our standard function based on the value of x of s plus the derivative set at that value times x minus xs. So that's pretty interesting that we can do that. What if we were trying to develop a model around something like, I'll grab a different color. What if we were trying to develop a model based off of a function f of x equals k x squared, where we're then going to be centering this around x equals x of s, and we're going to assume that k is going to be some constant. So in that setting, we would be able to say, okay, how would we linearize this function? It is nonlinear because it's x squared, so what can we do? Well, we can take this function to be true. Thus, we can say f of x is going to be approximately equal to f of x at s plus the derivative at x equals xs times x equals xs, which is approximately equal to, if we plug in the exact term, k times xs squared plus the derivative. Well, the derivative of that is going to be 2 times k times x, but it's going to be evaluated at x equals xs. So that multiplied by x minus xs. So in reality, we've turned our function to be evaluated at xs, except for a singular x that still exists. We can further take that and say that the linear approximation of this is k xs squared plus 2k x xs minus 2k xs squared. So we have those terms that have been expressed and pulled out. We can try and solve these directly for a singular term and then an x-bearing term. So we can say now that based on the x-bearing term first, that is only existing in 1, so that's going to be 2k xs times x plus, we have k xs squared minus 2k xs squared. And this now is a standard linear expression. This is going to well approximate for kx squared around the actual set point that we choose. So for whatever that set point value is, that is actually going to approximate it pretty well. But unfortunately, this is going to only end up being a linear line. So we have a slope and we have an interface set point value. So based on our intercept and our slope, we can only approximate that for so long. If we were trying to derive this and we plotted that out, we might get some function that looks like this. But when we then take whatever that value of x equals xs is for our function, we might ultimately find that because it's a line, it will work really, really well, but only nearby. So when we look at that, we see our line here. This is going to be our linear approximation, and it's going to go very well nearby. Little to no error as you move away. But the further you move away, the more error there will end up becoming. That's where the second orders, third orders, and so on of all the higher order terms are actually going to come into play and be really helpful. But for this exact point in value, it will actually approximate quite well. And we can plug in terms here. So say that we actually were to plug in directly that maybe k is equal to 1 and xs is equal to 2. Then in that setting, f of x is equal to 2 times 1 times 2 is 4x plus 1 times 2 squared is 4 minus 2 times 1 times 2 times 2. That's going to be 8. F of x is equal to 4x minus 4. So in that setting, we can in fact plot this out. And maybe that's actually what we ended up drawing just by happen circumstance, because the intercept value is minus 4 when x is equal to 0. Maybe that's what we'd end up hitting. But either way, this is how we would actually be approximating for that value in term. Looking at the board and seeing the challenges, I'm seeing for myself as a note that blue seems to work well up here, but down here it does not work as well. So I'm going to try and avoid using blue that low. But I'm glad that we have a couple more colors to work around with. In either event, this allows us to essentially state a model of expression for linearizing and approximating for what could be a challenging expression. And when we linearize for those and we put them into a transfer function, they help us to make a rapid-based assumption that we can then use for much easier calculations, decreasing the rate of speed that's needed to actually perform computation for our model. Let's say that we had multiple inputs. We just described it based on one input, but say that we had a function f of x1, x2, and so on until x to the n. Well, we can approximate a function like that in the exact same way. So we need to first consider the set point values for each of those. Therefore, that will be f based on x1 set, x2 set, and so on until xn set values. Then we can multiply that by 1, because this is based off of 1 over 1 factorial times x minus xs to the 0. Those are based on those set point values as well. So in that sense, we have our very first term, which is just we have our set point values that were preconditioned for each of these specific values of x. Now we can add that to the derivatives. Now, this is a multivariable function, so we're not going to use a full derivative, we'll use partial derivatives. And so we can now add that to the partial of f per x1 set at x1 equals xs multiplied by x1 minus its set value to the 1. We can also keep adding. So df dx2 at x2 equals x2s, x2 minus x2s, and so on until accordingly df dx to the n, xn equals xn to the s, and that will be your full function. And in this way, we have a way now of standardizing where f is built off of each of its parts multiplied by the actual change, where this represents the slope of change multiplied by that change-based value. So that's really all that we're doing, is we're generating a standardized intercept of our starting point, deviation-based changes, and the slope or rate of the change based on each of the parts of our function. And that's giving us our first order expression. So say that we wanted to take this and apply this to a standard function. Perhaps our function is going to be f of xy is equal to xy. And we know that we can take x equals xs and y equals ys as set points at any value. So in that way, we would want to apply this very much directly. So we can approximate this expression as f of those functional set point values. Well, that is xy. Set at both of those, that becomes xs times ys. Now we're going to add the first partial, set at x equals xs. So the partial derivative of this with respect to x is going to be, in this way, I'll actually write it over here. The partial of xy with respect to x is going to be y. And the partial of xy with respect to y is going to be x. And we can set those at their actual values. So based on their set point values that we have conditioned, that allows us to state this is going to become ys, because this is a set point slope. And I think I should have probably been more clear about that here, in that I'm trying to relate how it's actually occurring, the relationships, but we're still taking everything at set point values. So I could have just written x at x set point for whatever that would have been. So in this way, when it's now set at the set point, that means that this will become the set point value. This will be multiplied by x minus xs. Then the second partial is going to be dxy dy at the set point, which is now xsp, multiplied by y minus ysp. And thus, this becomes our actual expression that linearizes xy is now this, where everything is based off of separate pieces. So if needed, and we wanted to build out an expression, we now have x and y separated from each other. We can put y onto the other side if needed. We can look at these two terms separately. And if maybe this was z, and we wanted to say that z of, maybe it's of t, truly, is now equal to xs ys plus ys times x of t minus xs plus xsp y of t minus ys set point. Sp and s are the same. I just am using them interchangeably. So I'll make a note. That they're the set point. And this could be true. And so if we wanted to standardize and see how this function looks on the output, where we want to build a transfer function and see what component pieces they're based off of, we can do that. But in this way, we are truly just trying to evaluate what happens if there are multiple inputs and how that might change the function. But as we still see, we have these rates that we've defined based on our actual expression terms that have a deviation from our set point. And that should seem very familiar from this course to this point. So let's try and approach this with an actual model from our course so far. We're going to take a reaction system with one inlet and one outlet. We're going to have a volumetric flow rate of fluid that's going to be based on F in and F out. We'll have a concentration in and our concentration after. This is a CSCR, so there is a reaction where maybe we're going to have two A's making a product. Our system will have a constant volume, and let's make some assumptions here. Let's assume constant flow rates, volume, temperature, and reaction rate constant K. Let's assume as well that we're going to have perfect mixing in our system. And among that, I think for right now, that should be good for our assumptions. We can take, based on this 2A to P that we've already assumed for a second up there, that this is going to be a second order reaction, meaning the reaction rate is negative K Ca squared. Let's build out our overall mass balance. Accumulation is equal to in minus out plus reaction. For the overall balance, we're not really assuming anything's changing, and it's not reacting based on like nuclear reactions, so that'd be more on the basis of a component mass balance. We're gonna have 0 equals F naught times Ca naught minus FCA equals 0 again. And more or less, we're already assuming that fluid flow rate is constant. So for the overall balance, we're just going to be standardizing an assumption that for right now, these are going to end up being constant, where the mass flow rate in equals mass out, and our fluid flow rate is just going to be set as constant. For the component mass balance on A, we are going to go ahead and assume there is a reaction. So this is going to be d over dt for the mass of A, which is also known as the system volume times concentration of the system. V times Ca is mass. This will be equal to the fluid in, which is F now, and we're just going to say FCA naught. Fluid out, FCA, and we have a reaction term. So this reaction term itself is volume times reaction, but instead of doing plus volume times reaction, because the reaction has a negative, I'm just going to go ahead and do volume times the reaction already plugged into the expression. Now, volume is constant, so we can move that out of this derivative and leave it as this. There's a couple other things that we could do with it. We can go ahead and combine the F's here. We can play around with dividing things. But for right now, I think this is okay. I think this is a good expression. Now, notice though, if I asked you to build a transfer function based on our output, which is going to be our controlled variable, and our input is either mv or a dv, that would be really difficult. Why? The squared. Now, if there wasn't a squared, we could do this. We can move these two terms to this side. We can then go ahead and perform Laplace transform on everything. We can group it together to get it based off of our output over our input, and we can build that out. But because of this squared, that stands in our way. So what are the two things that we need to do first? Well, we need to linearize. And then we need to build out some dynamic variables. And after we build out our dynamic variables, that will allow us to more easily move into the Laplace space. So linearize, we're going to use the first order that we did. The dynamic variables means we need to take the steady state approximation and subtract. To linearize, we are going to take this expression in term, and we're going to go ahead and do that. So linearizing that, VKCA squared will be approximately its set point value. So VKCA squared standard. This is just going to be our assumption, as the set point is Ca naught and Ca, really just based off of an initial steady state that we could have. And remember that, steady state, that's our set. Plus the derivative of this with respect to Ca squared. So that's going to be 2VKCA. We're going to evaluate that at the steady state times Ca minus Ca naught, our change. And this is a good linearization approximation. Now, for 2, we need to consider, in order to get the dynamic, we need to do a steady state approximation. So to do that, we are going to go ahead and assume that we are at steady state for our component balance. Therefore, the left-hand side is 0. And this is equal to FCA naught minus FCA minus VKCA squared. But evaluating it all at steady state, we are assuming that these are true. And thus, we have 2 additional pieces that we can plug directly into here. We can take this term and generate out what we would need to do a Laplace transform. Now, remember, to get to the dynamic, we have to consider the transient minus the steady state. So I'll grab a different marker, maybe the pink one, and we're going to move on over in here to continue evaluating this expression. So if we take this out and we move this, we can assume v dca dt minus 0. And this is going to be the left-hand side. This is because we're taking the transient term minus the steady state term. And we know that is true based on these. That means this is just v dA dt. And based on that, if we wanted to pull these in directly together, we can actually do that directly here, because we can assume that this is v dt of 0, and thus that is v dca dt of our dynamic variable. Now the right-hand side is a little bit more fun, a lot more terms. So we're going to take them piece by piece. The first piece is FCA naught. We're going to subtract that by itself. And that'll yield FCA minus CA standard, which is FCA standard dynamic. And we're going to break this into right-hand side pieces because it might be easier. We're going to do the same thing with this second term, our outlet term. And we have the standard piece that allows us to now say FCA tilde, or dynamic. And our third term, our reaction, where this was in, out, and now reaction, and that was accumulation. Right-hand side, piece 3. This is our reaction term here. Now we've just linearized our reaction term. Let's not forget that. So our full reaction term, for right now, these minuses, I'm just taking the piece base value. That is on the transient side, VK CA squared minus VK CA squared based on our steady state, right? But remember, this first term we linearized as well, so we can actually change that. That'll become VK CA squared standard plus 2 VK CA standard, CA minus CA standard. I think in here I wrote a not by accident. That should not be there. My apologies. That's the first piece minus VK CA standard squared. And if you notice, this term cancels out. So we're actually just left with this inner term. We can put the whole pieces together, and in doing so, we would get left-hand side V dCA dt tilde equals our inlet term, which is F CA naught tilde minus F CA tilde plus these, which would have normally yielded the tilde term immediately, but now we can just actually incorporate that directly, which will be plus a minus. So either way, we could do now minus 2 VK CA tilde, because together this CA and CA naught becomes the tilde that I was looking for. And this becomes our dynamic expression. Now, of course, again, I could have just moved the minus out there, but either way, we yield the expression of interest that we would like. So let's go ahead and we're going to group onto one side our CAs and onto the other side our CA naughts. And so in this case, we're going to have V dCA dt plus F CA tilde plus 2 VK CA tilde. This is going to be equal to F CA naught tilde. Now we're going to go ahead and group these together. So that's going to become V dCA dt plus, we're going to pull out the CA tilde term to yield F plus 2 VK CA times CA equals F CA naught. Here, we are going to try and divide everything by this specific term that we now have. So dividing everything by this term, we will get V over f plus 2vk Ca dCa dt plus Ca equals f over f plus 2vk Ca times Ca naught. And here, we have a lot of terms to be working with. So instead of writing these out each time, we're going to go ahead and just call them the time operator, and we're going to call this a gain operator. For now, just gain proportional Kp. So in this way, we can rewrite this as T dCa dt plus Ca equals Kp Ca naught. This is a lot easier to perform a Laplace transform on. So I'm going to change colors, and we're going to perform the Laplace transform. That's going to make this side turn into T times S times Ca of S plus Ca of S equals Kp times Ca naught of S. We can group together our CAS terms on here to get Ts plus 1 times Ca of S equals Kp of Ca naught of S. And we can divide to yield our transfer function is Ca over Ca naught, both of S, which is Kp over Ts plus 1. And in this way, we have generated such an interesting transfer function. And we did it all from just our standard equation. And now Kp and tau are both previously defined as based off of flow rates, volume, rate constant, and initial concentration. So if any of those values change to another value, that'll change the gain or the time constant for our function. And using this transfer function model, this can help us to more easily evaluate our system. But this is all based off of our singular values for our set points. And those set points are going to be incredibly important as they are our linearization points. They are only going to allow this model to become accurate when we are in concentrations nearby, but when a concentration might get super far away from there, unfortunately, that may no longer work. And so hopefully this has been an interesting example for linearizing an ODE model to get a transfer function. I'm going to erase the board, and we're going to continue the lecture based on general procedures for obtaining process responses. We're going to talk about the general procedure for how we actually go about solving problems in process responses. So based on our course, we know that we're given a problem. We have to define the problem that exists and the assumptions. So we want to draw out the image. We want to see what are the things we're looking for. Can we define any of the constant variables, deviation variables, or manipulative variables? Then we want to perform mass and energy balances, followed by linearizing those balances when they may be nonlinear. We want to perform a transformation into our deviation variables by taking our transient minus our steady state function, and we want to perform a Laplace transform on that. That will allow us to rearrange for either our transfer function g of s or our output function y of s. We could perform calculations within either of those spaces, where maybe we have to do finite value theorem, and then once we do that, we can perform an inverse Laplace transform back into our y of t output. We can then return to our original variables from the deviation by just adding that to the steady state value. So where is this useful, and why would we want to use this? Well, based on the previous example, we derived more or less a first order system. Funny enough, we had a second order reaction rate, but that's not the system, that's the reaction. The system itself we described as a first order, where we had the output over the input as our gain over the time constant times s plus 1. And this allows us to see this term and learn more about the unique representation of any first order example and how we can define it based off of those two singular values. So, being that we've now learned a little bit about transfer functions and their purpose, what happens in a dynamic system? So if we have an input set here and we have an output, I've shown inputs in the orange and outputs in pink for a second, where maybe we have a step function for our input, where we go up and now we have a transient response that leads us back to steady state for output. We've defined that already using the gamma term. Additionally, we might have an impulse where it's at a standard value, it jumps up really quickly, goes right back down instantaneously. So that is a little bit more tricky to balance and to understand. I've already shown here, based on the inputs x of t, that we have some constant c multiplied by the step function. And as we go into the transient space of the Laplace, we have the ability to see that it becomes c over s from our table. Our impulse function, we have c times delta t. When we go into Laplace, it becomes just c. So how do we then see what happens outside of the function when we look at what's happening on our output? We just saw the input, so how is the output based on the same premise? So if we can use the initial value theorem and the final value theorem in order to really quickly study the initial and final time behavior for our output system. So in that way, what we can do is we can say, okay, time is going to be going on to infinity for each of these, and we're going to be looking at what's happening primarily at 0 from the right-hand side or the left-hand side. So let's look at our step function first. Looking at our step function and the response, we know that this is based on our system already. And we know that y of s is equal to x of s times g of s, our transfer function. And we're saying that we're going to be taking our first order system here, and we're describing on our first order system how our input affects our output. So our y of s is going to be equal to x of s, which is c over s, multiplied by our transfer function, which is kp over tau s plus 1. And remember, this is a model. It teaches us about how, based on that kind of model for our system, our input is influencing or affecting our output very directly. And so in this way, we would say that y of s is equal to kp times c over s times tau s plus 1. We can then consider, okay, well, how is this going to be going on for maybe the final value theorem? So if we took the limit as time goes to infinity for f of t, that is the limit as s goes to 0 for s times f of s. And in that way, we can actually see directly what would be happening as s goes to 0 for our system. Well, as that happens, that becomes the limit as s goes to 0 for s times kp times c over s tau s plus 1. Those s's cancel, that s goes to 0, and we get kp times c, where c in this case could be the delta x perhaps, for how much of our step function is influencing the value directly. And now what we can see directly is how the influences is going to occur and how much of that change is actually influenced based off of the amount of x that we've put into the system, which we've called c, as well as the gain value that we've actually represented in the numerator for our modeling transfer function. Now, based on this system directly, if we went ahead and performed an inverse Laplace transform, we would actually yield y of t is kp times c times 1 minus e to the negative t over tau times our step function. And the reason for the step function there is because that is based on our initial condition. I'm going to move out of the way for a second so you can see more easily. And this is because of what happens at exactly and before t equals 0. And so that is actually how we would then describe our model system for our output based on those conditions. But what if we had an impulse function? Well, for an impulse function, we're really more concerned about what's happening on the right-hand side of 0. And so we would use the initial value theorem. And while this was the final value theorem, we're going to use the initial value theorem to evaluate this, where this was the limit as t goes to 0 for f of t, which is the limit as s goes to infinity for s times f of s. And in that way, what we're really looking at and evaluating here is the same function, but we're going to take it on a different approach. Our f and y are synonymous here, so we're going to just plug that in directly, and we're going to see the limit as s goes to infinity for s times kpc over s tau s plus 1. Those s's cancel, but that s goes to infinity. That means that term is going to be much, much greater than 1. And so if tau s is going to be much, much greater than 1 as s goes to infinity, then what we really get out of the initial value theorem is kpc over tau. And that is going to help us to solve directly our Laplace transform as we go back, perform the inverse, and really yield for us actually now that y of t is going to be kpc over tau e to the minus t over tau. And now, why do we not have the impulse there? The impulse is left out because at this point we're only describing what happens on the right-hand side and the impulse has already occurred. But notice that this just yields our coefficient term. That's all we've solved for is the coefficient. That's it. We've stated, okay, we know the relationship here that the step function be described more easily based on this 1 minus e term, and that's based on our table. We have the same thing here based on our e expression as well. But we are relating this based off of what is the actual value or the total gain or the total change, which is based on that final value theorem or initial value theorem. This relates initially what happened here based on the impulse, what dramatic change occurred. This happens on a final because we're talking about what happens ultimately at the end. We know that as this goes back down, we're going to eventually reach a new value theorem, which we can also have performed there. But the point remains that this is getting us a generalized coefficient term to understand overall what might happen. And this is true because as time does go to infinity, we want to see what was the overall dynamics that may have actually occurred. So on that setting, we keep talking now about gain, which we've really tried to describe here a little bit more deeply what gain is, and that's how the amplitude might change or the overall effect. But we also need to consider the time constant. How do we interpret this time constant? What does it mean and how do we utilize it? So let's say, for example, that we use a first order system with a step function, and we want to identify when the time reaches 63% of its final value based on our step input. So to finish out the lecture, I rearranged the board, and using some of the information we just solved for about the step function, I just rewrote it up here. So instead of using c, I just go with delta x this time, and I defined already our x value as delta x, or the change in height, times our step function. Now we have the Laplace transform of that we can take. That will yield x of s, where that's going to be the delta x over s. And we have an output here that's relative based on our y. Now at time equals 0, this function occurs that allows the step to occur in the input, yielding to an output change that we see here. Now we've just described that using a first order model of our transfer function, that we were able to yield this expression in particular. Kp delta x, which is the total amount of change that will be happening here, times 1 minus e to the t over tau, which is our time constant, multiplied by the step function. So what is the time constant? What are we really looking at here? Well, let's consider a situation in which we want to ultimately solve for the time constant. And let's say that we want to solve for when t equals tau. Well, one way to do that is by considering perhaps what happens when we reach about maybe 62.7 or 63% of this value. So maybe that is about here. What is the time when we reach about 63% or 0.63 fraction of y? So in that way, what we would like to do is say, okay, well, we know that we're looking for when y of t is equal to 0.63 of itself. Thus, the overall effective change here of the total height that could ever be reached, that would end up being 0.63 of the end term times y of t as that goes to infinity. Thus, that would be the same as saying 0.63 times the final value theorem, which is Kp delta x. So we can solve then by doing the left-hand side as 0.63 Kp delta x equals the right-hand side, Kp delta x times 1 minus e to the minus t over tau times the step function. But we're on the right-hand side now. We're over here. And so over here, the step function itself is equal to 1. It is either 0 or 1. Thus, we're just going to go ahead and assume that on the right-hand side of time, this is equal to 1. And that's just based on a base value that truly this is delta x times x of t, right? Well, if we wanted to go ahead and just say it's delta x, and we already know the step is inherent, then that is 1. And that would make it to be equal to, ultimately, the delta x, which is already over here on this side. So we can then try and solve for these conditions. Kp delta x is on both sides, and we can then say, okay, well, 0.63 minus 1 is equal to negative. Thus, let's just move the e over. Make it e to the minus t over tau is equal to 1 minus 0.63. And then we can take the natural log of both sides, where we get negative t over tau is equal to the natural log of 1 minus 0.63. Well, that's the natural log of like 0.37, and that's approximately equal to negative 1. Thus, t over tau is equal to 1, or t is equal to tau when we are evaluating for this to be 0.63 of f of t, or 63% of our total. Now, we could have also done the opposite. I could have just said, what happens when t is equal to tau? What do we get? Well, we know that y of t is going to be equal to kp delta x, 1 minus e to the minus 1 times the step function. We know that's going to be equal to 1 still. Y of t equals kp delta x times 1 minus, in this case, e to the minus 1 is going to be, take the reverse of these terms ultimately, and we're going to get that as 0.37. Y of t is equal to 1 minus 0.37 is 0.63 kp delta x, which is exactly what we had stated before to be the truth. Now, had we gone backwards even further, we could have ultimately found that yes, we're looking for 63% of our final value. But what's really interesting about this is we're actually just describing what is happening as we're reaching these new steady states. So it takes about 63% of the time of which we go from the 0 to the final for our output in order to reach a new steady state value for our step function. And we can continue reaching new intermediate steady states that will allow us to ultimately reach maybe 95% and 99% and so on as we go from tau to 2 times tau to 3 times tau and so on. But what's super fun about this and interesting is for those who've taken statistics, this should kind of make you think about standard deviations. This should make you think, okay, well, based on a standard set value and deviations from that set, how long does it take to get to 1 deviation? How long would it take to get to 2 standard deviations and 3 standard deviations? And that's really what we're looking for, are based on average values and the deviation that which could occur from our set system. If we know what the average is that we're assuming, how many time-based constants will actually calculate or really capture mathematically our full function? How can we model that together? And so based on really any type of input value, if we have a model and a setting of our input, we can see how the output would change accordingly. And as we get into more complex systems, we may need to use other linearizations, which involve second or higher order degrees. We might have to consider output variables more in depth, or maybe even some error-based functions. So hopefully this has been interesting for you about seeing how we can linearize a general setting and understanding of solving problems, and really more about what some of these terms mean in terms of their amplitude or residence time, if you will, that will lead us into further calculations. So have fun.